When we think about the future of green energy, we're picturing electric cars, right? Massive grid scale batteries. But what if I told you that the way we make those batteries has a surprisingly dirty secret? Okay, let's get into this because a revolutionary new process might just be the key to making our green tech, well, truly green. So here's what we're going to cover in this explainer. First, we'll uncover that dirty little secret. Then we'll introduce the game-changing solution, going dry. We'll get into the magic material that makes it all possible, see who's actually trying to build this stuff at scale, tackle the challenges they're up against, and finally, look at how this one piece of tech could unlock the entire next generation of batteries. All right, so let's start right there with that dirty secret. We're talking about the hidden environmental cost of producing the very batteries that are supposed to be saving the planet. To really understand the problem, you first have to ask, how are the vast majority of lithium-ion batteries, the ones in our phones, our laptops, our cars, how are they actually made? Well, the answer lies in a process that's anything but clean. It's called the wet slurry process. So picture this. First, they take all the active battery materials and mix them into a pretty nasty toxic solvent to create this goopy paste or slurry. This paste gets spread really thin onto a metal foil, which is what becomes the positive or negative part of the battery. But here's the real problem. Those freshly coated foils have to go through these gigantic energy-sucking ovens just to bake off and evaporate the solvent. And then you have to capture and recycle that toxic stuff, which just adds more cost and complexity to the whole thing. And the impact of all that, it is staggering. For every single kilowatt hour of battery capacity made this way, the process pumps out between 57 and 92 kilograms of CO2 equivalent. It's a hugely energy-intensive method that kind of undermines the whole point of the technology in the first place. But what if you could just get rid of all of that? What if you could eliminate the solvent, the ovens, and a huge chunk of the cost and energy all at once? Well, that is exactly what the revolution of dry battery electrode technology promises to do. I mean, when you put them side by side, it's a night and day difference. The dry coating process is completely solvent-free. No solvents means no giant drying ovens. That drastically cuts down on energy use and shrinks the factory footprint. And this isn't just a tiny improvement. We're talking about cutting cell production costs by a solid 6 to 7%. That's a huge deal that could make EVs and grid storage way more affordable for all of us. And the environmental payoff? It's massive. If just 10% of all battery manufacturing switches over to this dry process by 2030, we could save 480,000 tons of CO2 emissions every single year. That's a truly global impact. So how on earth does this revolutionary process actually work? Well, the secret to making this whole dry thing work comes down to the magic of a pretty common polymer. It acts as the perfect binder, kind of like a glue, for all the dry powder materials. And that material is polytetrafluoroethylene, or PTFE. And you definitely know this stuff. You just know it by another name. It's the coating on your nonstick frying pan. Turns out, this unique polymer has a special property that lets it act as a super effective glue, holding all those dry battery particles together without needing a single drop of liquid solvent. It happens through a process called fibrillation. So you start with a simple dry mix of battery powder and PTFE powder. Then you apply what's called shear force. Just think of it like you're kneading dough or using a rolling pin. That physical force actually stretches the little PTFE particles and causes them to unravel into this whole network of tiny interconnected fibers. These fibers form a microscopic spiderweb that physically tangles up and binds all the other particles together, creating a strong, flexible film, all from a dry powder. Now, this isn't just some clever trick in a lab. There is an industrial race happening right now, with major companies all trying to figure out how to scale this tech up for mass production. And two main approaches are really leading the pack. First, you've got the Maxwell type process. It creates a thick, self-supporting film of the material first. Then, that film gets pressed down to the perfect thickness and stuck onto the metal foil. The other big one is Dri-Treat technology. Instead of making a separate film, it forms the film directly onto a big roller, basically a high-pressure rolling pin, and then immediately transfers it to the foil. With Dri-Treat, that delicate film is always supported by machinery, which could be a huge plus for high-speed manufacturing. But of course, no revolutionary technology is ever that easy. There are still a few key hurdles that researchers are working hard to overcome to really perfect the dry-coated battery. So, the biggest challenge is something called the anode problem. See, on the positive side of the battery, the cathode, PTFE is perfectly happy and stable. But on the negative side, the anode, it runs into big trouble. When you charge the battery, the PTFE can actually react with lithium ions, and that reaction literally destroys that binding spiderweb of fibers we talked about. The whole structure of the electrode just falls apart, and the battery's performance completely tanks. But, and this is the really cool part, scientists have already come up with some incredibly clever solutions. One idea is to coat the anode particles with a tiny, protective polymer layer. That alone boosts the efficiency from a terrible 47% all the way up to 84%. Another trick is to add a special chemical to the battery's liquid electrolyte, which basically forms a protective shield. A third way is to just use a blend of binders, mixing PTFE with another polymer that'll hold things together even if the PTFE starts to degrade. The main takeaway here, this problem is solvable. And solving these challenges is absolutely critical, because this dry coating process isn't just about making today's batteries a little bit better, it's about enabling the next generation of batteries. Specifically, dry battery electrode technology turns out to be a perfect match for what many consider the holy grail of energy storage, solid-state batteries. And hey, you don't have to take my word for it. The researchers from our source material put it pretty plainly. Dry processing is a perfect solution for solid-state batteries. So this isn't just a nice-to-have improvement. Experts see it as an essential, enabling technology. And here's why. In a solid-state battery, that liquid electrolyte that ions swim through gets replaced by a solid material. Well, a lot of these promising new solid materials are extremely sensitive to the moisture and solvents used in that old wet process. The dry process completely dodges that problem. It also lets you make much thicker electrodes, which is the key to getting that massive jump in energy density that solid-state batteries promise. And finally, because you're not using any solvents, the dry process preserves that really tight particle-to-particle contact that's absolutely essential for ions to move efficiently through a solid structure. So, it all brings us to this one final question. We started with this complex, energy-intensive, solvent-heavy process, and the solution? It seems to be a remarkably simple idea. Just mix the powders dry. So could this one, seemingly straightforward shift in manufacturing be the key that finally unlocks a truly sustainable energy future? Well, it just might be.